Okay, first, do you want to just like introduce yourself and like what your job is and then what your background is in Chelan County, whether I know you already did a talk for WRI.
hmm Yeah, my name is Brock Burghardt. I am a meteorologist. I have a PhD in atmospheric science meteorology, or sort of essentially the same term of science of studying the weather. I'm also a certified consulting meteorologist through the American Meteorological Society, and I do work in helping people and companies understand how weather impacts them, how it's impacted them in the past, how it's going to impact them in the near future, and then planning from a longer term climate perspective of how weather will impact them in the future.
So probably for most people in Leavenworth, those mid-December weather events, they didn't see them coming. Now, would you say there were any warning signs, the summer before or trends leading up that could have influenced that? Because obviously a lot of it with like the amount of water saturation was just directly related to the weather of late, but were there any trends that you think contributed to it?
Yeah, that's a good question. And some of it gets a little bit out of meteorology and was what I had heard some folks suggest too, helping out with some of the cleanup actually after that damage in Leavenworth. And I guess sort of like setting the stage for all of that was that 2025 was a really warm and really dry year. Especially the spring and summer was one of the driest, one of the warmest. And so there was some suspicion, and this gets a little bit out of my wheelhouse, but was there pre-existing stress on some of the trees because they had been stressed from the lack of water during um, that long period of time? And then, of course, leading up to the event, there was, increasing confidence, um, beginning, a few to almost a week out, that there was a pretty active storm cycle happening. And really, the strong signal was the potential for really heavy rain. I think what continued to increase leading up to that was just how warm things got, and how much rain fell, and that kind of combined in a couple of ways. One, it allowed the rain snow line to get really high, upwards of 8 to 10,000 feet, which in winter is an abnormally warm storm. So the rain was falling to 8 to 10,000 feet above sea level. So what that did was while we didn't have a great start to our winter snowpack, we did have a start to our winter snowpack. Um, Up around Stevens Pass, there was a few inches of snow in the form of liquid equivalent. So the snow that was up at Stevens Pass, if you melted it down, there was a few inches of water up there already. So it got really warm. You had a bunch of rain falling, even up at the passes. That led to just a lot of water falling into the ground, rushing off into streams and rivers. So that's why we saw a lot of river flooding. And of course, that led to very saturated grounds. The wind event within Leavenworth was a bit of a surprise. I think in hindsight, it did have some warning signs in terms of as this storm cycle was starting to come to an end and it was sort of dropping to the south, there was a very strong jet of low to mid-level winds that was on the order of like 60 to 80 knots. So that's something around 70, 90 mile per hour winds that weren't too far above the ground. And that's not overly uncommon to see that strong of winds, but what gets really tricky is in a lot of Chelan County, north central Washington, and Leavenworth especially, is how the winds are going to interact with complex terrain. We know that the Cascades are very jagged. You have this ridge, it goes down into a deep valley, goes back up to a ridge. That can make it really complicated to understand, is there the potential for downsloping or a mechanism in which those strong winds can actually be directed from near the ground, the 70, 90 mile per hour winds above the ground, be directed down towards the ground. And that requires a very um, a very delicate setup of the temperature profile in the low part of the atmosphere, and then that wind profile as well. And those came together to produce what we call a mountain wave that was breaking and mixing down the really strong winds right down to the ground in Leavenworth. Typically, when we see these types of setups, they tend to also impact areas in and around Wenatchee as well, and we didn't really see that as much. This was really localized on the particular evening that Leavenworth was hit by these strong winds. So it was a bit of a surprise. The National Weather Service ended up issuing, I believe, a wind advisory, a high wind warning after the winds had already started. So there wasn't a lot of forecast confidence going into that. There were setups for additional strong wind events that didn't materialize quite as bad as they could have in the days following. So it was sort of a kind of caught forecasters off guard, but we're a little bit better prepared for the coming days. So it was just one of many aspects of this really strong storm cycle.
So, just to clarify, like that very last thing you're saying, are you saying the windstorm could have been even worse than it was?
Yeah, I think what stands out, in my mind was that, Leavenworth got this damage. Um, I was rather surprised that it didn't impact areas around the foothills of Wenatchee. Typically, when we get these types of setups, you will see a broader area that are impacted by winds. And we did see, I believe it was 2 to 3 evenings later, we did see a really strong cold front push through. There was concerns that some of that really strong wind would mix down. It happened a little bit, and we saw pretty broad um, high wind reports across a lot of central, southern, and eastern Washington. It wasn't quite the intense. It doesn't appear to be quite the intensity that happened within Leavenworth. But Leavenworth is just a very localized event, which was a little bit surprising to me. I think we don't fully understand. I think it was something very. There was just a very particular setup that interacted with essentially the crest of the mountains right behind Leavenworth to the west there that allow those winds to break just there. Because typically those types of setups would also lead to breaking of winds that would um, slope down into the foothills of the Wenatchee Valley as well, which we didn't see on that evening. So it was very localized to Leavenworth, which I think was part of why it was a bit of a surprise. It was a very anomalous event in the fact that it was so localized.
No, it definitely was. People I know in Wenatchee just woke up to like another day. So, this little corner of the Pacific Northwest outside of continuous fire danger tends to be pretty isolated from natural disasters. Like we've had a flood before, but like that's not what people typically think of. And then when you go to the 90 to 100 or like 90-degree winds, or sorry, mile per hour winds, I think to a lot of people that's like Tornado Alley. That's not something that would happen near the mountains in Washington. So would you say that's like type of wind that's totally unheard of, or is it just not something that regularly happens?
Yeah, I think that's a good way to sort of set up that question of, was this is this something that's totally out of the blue? Is this something that can happen? I think it's something that can happen. There are certain mountain ranges that do get downsloping and breaking mountain waves that can really create very strong winds. This happens more regularly on the east side of the Rocky Mountains in Montana. They've had some very significant downslope wind events in Montana throughout this winter. This happens on the lee of the Rockies in Colorado as well. Boulder, Colorado, for instance, has had multiple windstorms, with winds sometimes gusting over 100 miles per hour. We see this with easterly winds and actually downsloping across the Santa Ana Mountains. That creates these Santa Ana downsloping and sometimes fire events across Southern California. So there are specific, and this was kind of was mentioned before, there are certain situations where when the temperature profile and the wind profile is just right and it aligns with the topography of the mountains, that those really strong winds aloft can get directed and actually enhanced as they come down to the ground. Very small differences in the winds or temperature profile above the ground can play a very large role in whether that does happen or doesn't happen. So it always is a tricky forecast for forecasters to look at these things. For north central Washington, for Leavenworth, it's less common. And the reason it's less common is that the topography is so steep. So it actually kind of does act to protect a lot of north central Washington, and towns like Leavenworth are actually sort of protected because the mountain is so steep. It doesn't really allow that wind to doesn't have time to sort of break down to the ground. It kind of just overrides and shoots over town. That happens more times than not. In this case, it did happen to mix down to the ground. So I think it takes a very particular setup for that to happen. Um, you hinted at this, and one of the reasons we don't really well understand this is because it is a rural area. And another association with that is that we don't have a lot of weather observations in north central Washington. We do not have enough. We have a couple of airport, what we call ASAW stations. Those are very reliable. Those are great. We have a couple of Forest Service fire weather, what we call RAWS stations. across the mountains in north central Washington, but we don't have any reliable weather stations. In and around Leavenworth, those being that are, high-end instrumentation, they're regularly maintained and calibrated. That doesn't exist. So even when we look back what happened in Leavenworth, there's no evidence really of what was the magnitude of wind. We're kind of just guesstimating based upon what the winds were above the ground, based on some of the damage that we had seen. But it's a very crude approximation. We still don't know what that was, but it also doesn't allow us to develop what we would say a climatology. So we don't know, was this a 1 in 25 year event? Is this a 1 in 100 year event? We don't really know that very well because we can't even quantify it with the lack of observation. So I think that's one of the trickiest parts is when we do see strong wind events in north central Washington. A lot of times we'll hear about the down trees, we'll hear about the impacts to infrastructure, to people, but we don't have a weather station often close enough to sort of tell us, hey, this is actually how bad it was. And if we can look and that station's been around a while, we can look back and say, okay, well, how often does this happen? What direction does that tend to come out of? How strong does that tend to get? We really don't really know very much of that because just the lack of observations.
Right, yeah, that makes sense. Like I interviewed Pat Fromm, who he has like some fields outside of town that like flooded, and his family heritage goes back into the homestead days. So he can tell
Wow.
you exactly when he had flooding, what happened, but that's not the same as having an actual weather station that you got data. Like he can
Mhm.
recount it throughout his whole life, but that's not really data. That's just his anecdotal understanding, which you would need the data to know the weather patterns.
Yeah, and yeah, and you're right that flooding is a little bit different because it's we do have some river gauge data on the Wenatchee River, and that's been around for about I think going back to the 1970s because I actually looked at how this event had compared to past events, and I think it actually came. Let's see, this event was the third highest crest on the Wenatchee River at Peshasta, and it was about let's say 9 inches short of the all-time record, which was November of 1995, and then there was another one that was about a half inch higher in November of 1990. So we can get some sense, and that, even that anecdotal, if it's recorded well, can give us some sense of I think a lot of folks said this is so crazy that this happened in December. When I looked at it, I said, okay, well, when I look at all the data for the Wenatchee River that we do have, um, a lot of the really big flood events actually have happened in November and December. Of course, a lot tend to happen in the spring melt off, typically more in May. And the frequency is such that it tends, if you're going to have moderate to high end flooding, it more than likely is going to happen in May in the spring versus the fall. But when you do have the really big flood events, they do tend to happen sort of in this late fall, but really early winter period. So it's not totally unusual. I think we have some semblance of the return interval and when these can happen on the Wenatchee River in terms of flooding. But yeah, on the wind, it's like you really need an actual weather station has an anemometer on it that's recording wind, and you can begin to develop climatologies of, how often do you hit 50, 60, 70 miles per hour that we just don't have.
Right, right. That makes sense. And then you sort of talked about how with the wind, the mountains can kind of have a compounding effect that sort of exacerbates things and makes winds more fast. Except you said, typically because it's steep, that doesn't happen. Sort of in my mind, just from a dilettante perspective, right? If you're gonna get crazy winds, it's gonna be somewhere like Kansas where it's the Plains, or it's gonna be like certain places in the Rockies where there's a big basin for there to
Mhm.
be like wind because there's nothing to block it. But you're also saying, like, I mean, you went into it before, but just, maybe to clarify a little for someone who doesn't have a knowledge, a mountain like that can also like build the winds instead of just blocking them. Like, does the wind go over the mountain or how does that work?
Yeah, no, that's a good question. And yeah, more times than not, the wind kind of just goes over the mountain and it does its thing, and we don't even really notice. That's probably 99 or more percent of the time that the mountains are there, and sometimes it will create as the wind hits that mountain. it will kind of rise up, it'll rise back down, and it creates this mountain wave. And we actually see the reflection of this sometimes in these mountain wave clouds that are called lenticulars. And we see these in central Washington fairly often, especially I would say in the sort of late fall and especially early springtime where there's enough moisture at mid-levels of the atmosphere to sort of represent these clouds kind of show up, and they kind of look like UFOs. They're called lenticulars. They look really cool, and they tend to happen above or just downstream. So if we have westerly winds, you might see them right above the crest of mountains, but then you might see them further east above the Columbia River, across the Columbia Plateau as little displaced. And that's just because the wind hits that mountain range, goes up, and then it kind of reverberates. It's essentially what we call it's like a gravity wave, and it's essentially like waves on the interface between the air and the water. It's pretty similar to this because the atmosphere is a fluid. It's just a very low viscosity fluid. And when there's differences in temperature through the atmosphere, which there often are, you can get these gradients that allow for these wave-like structures. As the wind hits the mountain, it sort of deflects up and then it kind of needs to oscillate until it gets back to equilibrium. And, that happens almost all the time. We just don't always see it. But if there's enough moisture, we'll see these mountain wave lenticular clouds. And then in very rare cases, when there are very strong winds at and around mountain level, and those winds are kind of continuously increasing above the ground and up to the mountain crest height. And then we have what we call an inversion, where temperatures are actually getting warmer as you go aloft, which can happen, especially in the winter months. When those two are just right, the winds are increasing with height, the temperature is increasing with height. You don't want the temperature to increase too much. It's a very delicate balance. But when those come just right, then basically the winds go up the mountain, but they actually get pulled back down and accelerate and then crash down to the ground. And they don't just kind of oscillate back. It actually crashes down to the ground and then brings those strong winds, and it can actually be enhanced further as they come down the mountain. Um, the frequency of that happening doesn't happen very often, and it doesn't happen very often in the Cascades again because the slope of the mountain is also another factor. So when it's a more gradual slope, like you see in parts of the Rockies, the Santa Ana Mountains of California, that is more favorable for downslope windstorms. The steepness of the Cascades makes it less likely, but it doesn't rule it out. So it tends to protect us, but it doesn't always protect us. So I think when it happens, it's less frequent, but it can
Hmm.
be just as severe, and I think it maybe can catch us off guard because it happens a little less frequently than it would happen in Colorado or Southern California, as an example.
Yeah, that makes sense. And then talking about how in this particular time, uh, we did have the mountains have an effect, and you mentioned the steepness. So, do you think, to your best approximation, in this case, like, did the steepness make things worse? Like, if you think about a little kid going down a slide that's not very steep, it's going to be less slow than a really steep slide. So, do you think in this case, since there was the weather event, if the mountains were less steep, it would have been less severe, or is it impossible to say?
I think it's pretty difficult to say. Yeah, I think that's a very good question, but I think it's difficult to say. If anything, um, for that particular event, I'm not sure. But what I can say is that if the mountains weren't as steep, we probably would see more downsloping. We would see more events like this in Wenatchee, in Leavenworth. Um, yeah, that's a very good question. It's hard to say in this particular event just because we don't have a lot of data. I still don't fully know whether this was a downsloping wind event or a breaking mountain wave. They're very similar, and we kind of classify them as one thing. Um, and overall, that's fine. But yeah, it's so difficult to say in this situation. But can say that yes, if it is sort of a saving grace for us, but it doesn't protect us all the time. Because if they weren't as steep, then yeah, we probably would see the frequency of downslope windstorms that are more similar to like what Boulder, Colorado experiences, parts of Los Angeles, experience.
Yeah, yeah. And then, so in like particular let's see with like the warming specifically, that's a part that contributed. Like at midnight on December 11th, it was around 44 degrees Fahrenheit, and then later that day it peaked at 49 degrees Fahrenheit at Stevens Pass, like not in the valley, which is pretty high for uh for the pass,
Mhm.
like not the valley. So how did the temperature in particular contribute?
Yeah, no, that's a great question, and that actually sets up very well of how this set up. So, what happened was you had this very warm air that was initially above the ground. So, if you went high enough up, if you went to the mountain passes, you would experience this really warm air. What happened was down in the river valleys, in Wenatchee, Chelan, in Leavenworth, the temperatures were still cooler, warm for winter, but cooler. I think we were still like upper 30s to 40s. So that is a strong temperature inversion, and that's what I was mentioning before, where if the temperatures increase with height, that actually forces the winds to sort of more volatilely. They become more volatile as they interact with the terrain because it allows it. It does a couple of things. What it can actually do is that it actually creates a lid above the mountain. So when the winds hit the mountain, they can't really rise anymore because of that inversion. So it sort of traps. And when you trap um, wind into a more confined area. We see this like under underpasses. Why we say don't take shelter in a tornado under underpasses because we actually have observed winds get stronger in underpasses. When you force wind, it's the same thing in a river. When you look at it, when the water gets forced between two rocks, you'll notice that water starts going a lot faster. It's the same thing when we have warm temperatures aloft, cold temperatures at the surface in the river valleys. That wind actually is going to accelerate, and then that inversion is also going to act to allow the winds to oscillate and then oscillate back towards the ground. So it's sort of a double whammy when you have the really warm air aloft and the cold air at the ground, and you have strong winds within that layer, that it's going to accelerate and then it's going to get directed towards the ground. Again, it has to be just the right combination of that temperature increasing with height. Um, that you need that to actually get directed back to the ground. And it helps if the winds aloft are already really strong, which in this case were. So both of those sort of checked the box for this event. And yeah, I actually didn't look at the temperature at Stevens Pass. That's actually a very good observation. The fact that like it was already sort of observed because what we saw was later that night in Leavenworth and Wenatchee, the temperature I think actually rose like into the 40s and 50s, I believe. Got really warm. So what happened was um, that mountain wave sort of acted to bring down enough warm air, and eventually that warm air was able to mix down and sort of scour out that colder air stuck in the river valley. Um, but before that happened, that inversion was sort of like what set up the mountain wave to bring the winds to the ground.
Right, for sure. And then sort of back to the flooding, like you talked about like the lack of data. It's like for example, Icicle River data on uh like the peak of water doesn't go back before the century. It looks like uh at least on ecology.wa.gov, it began in 2007, and this December 11th, the peak was it was the peak for when they have data of like 15.2 feet. And it's like obviously that caused flooding, but it wasn't severe flooding where every house was underwater. I think from some people's perspective who were on the west side, they were maybe thinking, "Oh my gosh, is everything underwater?" But what made it so the flooding wasn't worse? Do you not know the factor that made it so Leavenworth wasn't totally underwater? Is it because of, the rising topography?
Yeah, no, that's a good question. And I think it's very helpful to think about it in the context of what has happened and also in the context of what does climate change mean for this as well. To think of like, okay, why wasn't this worse? How could this be worse? I think, you know, what we know happened was we had this really warm event come in. And that warm air helps melt the snow. The rain helps melt the snow. So you have this really warm, strong, what we call atmospheric river come into into Washington. It actually came in multiple rounds, and that brings a lot of rain. And the rain is one factor, but when you melt off the snow up in the mountains, that's another factor. I think, it actually was a saving grace that we didn't have a more active start to the winter. It was we were sort of behind And that's early winter, but we were a little behind on where we should have been snowfall wise leading up to that big melt off and rainfall event. We had one storm over Thanksgiving weekend that had contributed a few feet of snow, high up in the mountains, and that is what melted off. Had we seen an early start to winter, we had, 10 plus feet up on the passes, and there was not only, 2 to 3 inches of liquid equivalent. When I say that, I mean when you melt, how we measure the snowpack typically is what we call SWE, snow water equivalent. That was around 2 to 3 inches at Stevens Pass. So basically, that says you basically had 2 to 3 inches of rain in a way that was stored as snow that melted off, in addition to all the rain that fell on top of that. Had we had an average winter, that probably would have been double that. And that would have been even more input into the river systems. It all starts up in the mountains and all, like you said, gravity, it all flows down. So, it was a lot of rain, especially on the west side. It was still a lot of rain. I think it was close to a foot of rain over a week around Plain, just north of Leavenworth. So, we don't have a good sense of we know that these warm, rainy events can happen in November, December. It seems like it happened back in 1990. We know it happened in 95, and they were a little bit higher. So I don't know specifically whether that was more rain or was there more snow melt off, but I think that's a very careful consideration of when we see these events coming. And this was what the forecast of the National Weather Service were looking at, was that this is going to be a combination of rain and snow melt, but it's something we always have to be cognizant of is how much snow is sitting up in the mountains. Like we rely on that slow melt off to help, replenish our rivers and reservoirs in the spring and summer months, but it can sort of be, it can be a hazard if it melts off too soon, whether that happens in the spring or these winter events. I think it's a larger hazard in the winter months because we can get these really strong atmospheric rivers that have a ton of rain with them. That those kind of have the bigger potential to be really rapid melt off with a ton of rain. But we don't really know, like you said, there's not enough data to say, does this happen once every 5 years? Does it happen once every 50 years? Has there been a way worse one that happened 100 years ago that we don't know about? We know that climate change is, increasing the frequency and intensity of some of these atmospheric river-like events. And, that does increase the chances that we could see, slightly increased chances for additional events. And, maybe instead of happening once every 15 years, it's happening once every 14 years or something like that. And maybe the severity is a little bit higher as well. So there's a lot of unknowns there, but the way we try to understand it is we have observations and we keep those observations going. We want long-standing observations. And then we try to do our best with researching and looking at what the climate forecast data tells us as well.
Right, right. So sort of second to last thing I'll touch on, we
Mhm.
had like you mentioned, the drier summer last year and we didn't have, we had the flooding, but it's not like we had a ton of s snow this year. And I think a lot of people are wondering, as we're entering into tourism season again, like, hey, is there gonna be a bunch of fires again? Will that affect my home? Will that affect my who comes to my business? Do you think we can have a good approximation of what the fire risk is and where those fires would happen, or is it too soon to say?
Yeah, it's a really good question. I've had a lot of people ask me, you know, the ch- these patterns tend to happen over the course of years. We sort of are in this relatively dry pattern. We've seen most, not all of Washington being designated in drought status. I think the last 3 or 4 years we've been having some pretty dry years. So we've been in this drought-like pattern. That doesn't mean that we don't get heavy rainfall events in between that sort of, help make the drought not worse. But we have been in this dry pattern, and we've seen, especially last year, a fairly active fire season. And part of that was we had a lot of lightning that happened last August and September as well. As we look at this summer, yeah, we're going into this with pretty low snowpack. We didn't reach our full snowpack. We're melting off our snowpack pretty early. We've had a couple of later season events that have helped to replenish that a little bit. Um, but yeah, the earlier we melt off the snow, especially from a forest, when we think about our big timber fires, our forest fires, grass and brush fires are a little bit different. those actually can have an inverse correlation to precipitation, where if you have a lot of rain, that builds up the grasses and brush, they're able to grow. And then if you have a really dry summer, now you have more what we call fuel loading, and your grass and brush fire risk can be higher either that season or into the following season, if it becomes really dry. The trees, the heavier fuels that create these big timber fires, those typically are, coming from longer term drought. So, a lot of the timber was, drier than usual. We saw this in a lot of the way we measure the fuel moisture in these, was quite very dry last summer, especially by the end of the season. And we're going to go into the season probably in a pretty dry state. And the what's really going to make or break this fire season is, I would say, there's chances are leaning towards it being a more active fire season. Of course, there's so many factors of, humans cause ignitions, lightning causes ignitions. Those two, we don't really know what's going to happen. We know that the fuels are likely going to be drier than usual, especially the heavier fuels, the timber. Um, but what can really make or break a fire season is, can we get any rainfall events throughout the summer season? Because if we can get just a little bit of rain intermittently, that can make a huge difference. We typically don't see that. Our summers tend to be pretty dry in north central Washington, for example. And I guess what is concerning too is it's not just north central Washington. A lot of the West is very, very dry. So I don't think that all the West is going to have intermittent rain in the fire season, is going to be normal or below average. I think it's probably going to be above average in net for a lot of the Western US. Um, it's really going to come down locally is, can we get some, at least light rainfall events throughout the summer? Because I think what's going to happen is there's going to be so many areas that are dry. There's going to be so many fires that it's going to be probably a competition for resources, especially as we get towards late summer. I hope I'm wrong and like there's a really good monsoon season that gets the Southwest a lot of rain and we get a really active rainfall season for the summer. But it's sort of a catch-22 for our rainfall events and the Cascades, is they tend to come with lightning as well, which we saw last year. We had, a setup for rain, but it was a lot of what we call dry lightning. The rain wasn't reaching to the ground, so you just had lightning conditions, and that rain wasn't actually providing any relief to the really dry timber. So, yeah, I guess in summary is we're leaning towards having probably an active fire season, but it's going to just come down to, can we get some rain in the summer months to help keep that fuel moisture up a little bit.
No, yeah, for sure. And then last thing, so sort of, climate change, we used to call it, well, people used to colloquially say like global warming, but global weirdness is probably a better term because it's not just things that are directly related to warming, like fires or decreased snowpack. We see some places, hey, they have more snow now, and they didn't. We just see a more frequent occurrence of all sorts of unusual weather events. But there's definitely a difference between weather and climate. Like, how much of the flooding event and windstorms last year can we like attribute to climate change, and or can we not determine if it was just a freak weather event? And then how likely do we have a certainty of how likely we are to continue to get disasters in the area due to climate change?
Yeah, yeah, no, that's a really, really good question. So, um, I'll start that with sort of defining, and you actually set this up very well. Weather and climate are different, but they're also the same thing. So, weather is what we experience on a day-to-day basis. It's the warm sunny day, and then a strong cold front comes through and it gets cold. It's just the changes in weather that we experience. Climate is just the average of all that over long periods of time. And I think that's really important to keep in mind, is that weather is always still a part of climate, and climate is just an aggregate of the weather. Yeah, and so there's been different definitions for it for various reasons, all of which I'm not entirely aware of, but we sort of generally call it climate change, but climate weirdness is I think is just as applicable, because there are things that we are very confident in. We've seen in observations and projections that align with what we've seen so far. And we know, that global warming, due to anthropogenic forcing, the emissions that we create, directly or indirectly as a human species, creates this greenhouse warming effect that is increasing average temperatures. Now, we can still see areas that have cold periods, But on average, when we look at a global scale on an annual basis, we see that we are continuing to warm and we know that we're going to continue to warm. So the east coast of the US just had a quite cold winter. When you look at the aggregate across the US, a lot of the central and western US had a very warm winter that sort of overrides that. And when you look globally, it was still quite warm. So that can make it, I think, challenging for folks to sort of grasp and understand that, the weather this winter was colder in one area, but when you look at the bigger picture lens, it's still well above average. So we know that temperatures on average are going up. We know that variability in precipitation is increasing, and we call this this has been kind of termed by a recent paper that eloquently sort of stated this as hydroclimate whiplash, which means that the frequency, intensity, and duration of droughts is increasing. The frequency, intensity of heavy rainfall events is also increasing. And, I think this is very palpable, especially out west, what we just saw last year. We went from this very dry, warm period to this very wet period. I mean, we got a large portion of our annual rainfall last year happened within a few days, within 1 week. That really is sort of the definition. And it's not that that hasn't happened. That always has happened, but the frequency intensity of it is increasing and it's going to continue to increase. So, it's like we should expect this, but it doesn't necessarily mean this upcoming winter we could see something similar, but it doesn't necessarily mean that we will. But we probably will see something similar within the next 10 years. And, it's just that the probability of that happening any given year is increasing slightly. So there's just a lot of statistics that are, and it makes it hard because, we might experience it twice within 5 years and then not experience it for 25 years. And part of that's just the natural variability of this very complex system we call the atmosphere. And there's a lot of, as you alluded to, second and third order effects too that we don't really well understand. Um, there does seem to be some um, evidence that you can get these really late, big, late season snowstorms. And we've seen these out in the Midwest, we've seen these out east, and it seems to be okay. Is that the temperature is warming, but there's more moisture in the atmosphere. So when it's just cold enough, you can get these really big snowstorms, which seems counterintuitive if the temperatures are going up. But it's just this really complex interaction. And the same goes for severe storms. We're actively trying to figure out why has there been such active severe weather seasons across a lot of the central US in the last 5, 6 years. Um, so there's a lot of questions that when there are multiple factors come into play, it's really tricky to say. I think we suspect that there are some climate change reasoning for that, but the attribution is really difficult. That's a very rapidly evolving area that we're getting better at. Oftentimes, it takes months or years after the fact that we can say Hurricane Harvey in Houston was something on the order of 20 to 40% of the rainfall of that major flooding event down in Houston back, I think it was in 2017, maybe. Was due to climate change. So without climate change, it still would have been intense, but it wouldn't have been as intense. So we're getting to that attribution where we can say it made this event this much more likely, or it made this event this much more intense. That I think is helpful because climate change doesn't necessarily create the weather events. It doesn't create the hurricanes, but if the ocean temperatures are really warm because it's been a very warm period, that increases the probability of it being more strong. So I think that differentiation is really important. But it is tricky. This is just inherently a very large, complex field. And trying to communicate it is one of the great challenges.
No, yeah, for sure. Well, is there anything you'd like to add or clarify?
I don't think so. No, you had some, I can tell that you thought this out very well. Your questions were very well set up, very pointed and very practical, to talking about what happened in North Central Washington. So, yeah, I think you did a really good job of covering sort of the fire aspect, the wind aspect, the flooding aspect, the climate aspect. Um, nothing from my side.
Yeah, yeah. Well, thank you so much for your time and being willing to talk for a full 40 minutes. So,
Yeah, no, I love. No, I appreciate you reaching out. It's really cool that you're putting this together. I love talking weather. So yeah, if you have any like clarifying questions, like hey, what about this, or hey, can you reword this? Feel free to reach out. I'm happy to respond via email, and if there's other future projects, happy to talk again.